Imagine waking up one morning to find headlines screaming, "A new ice age has begun." You look outside, expecting to see familiar sunshine, but instead, there's a thick blanket of snow, harsh winds, and freezing temperatures unlike anything you've ever experienced. While it may sound like a dramatic scene from a Hollywood disaster movie, scientists are increasingly asking the question, could this scenario actually become a reality in our lifetime? We've all grown accustomed to hearing about global warming, melting glaciers, and rising temperatures. It seems almost unimaginable to think that the Earth could suddenly shift towards a colder climate. Yet, history reveals a chilling truth. Our planet has regularly experienced cycles of warming and cooling, plunging humanity into ice ages that drastically reshaped life on Earth. But what exactly is an ice age? Simply put, an ice age is an extended period of time when global temperatures drop significantly, resulting in massive expansions of continental ice sheets, glaciers, and severely colder climates worldwide. During these times, the Earth's landscape transforms dramatically. Vast areas of land become uninhabitable, species go extinct, and human civilizations are profoundly disrupted or forced to adapt to extreme environmental changes. The last major ice age ended around 12,000 years ago, but the Earth has continued to experience smaller cold periods, including the famous Little Ice Age between the 14th and 19th centuries. Could something similar, or even more extreme, occur again soon? Today, scientists and climate experts are closely examining signs that suggest Earth's climate may not be as predictable as we once thought. In recent years, unusual cold spells have stunned people around the globe. Unexpected snowstorms in deserts, record-breaking freezes in typically mild regions, and sudden temperature plunges have raised eyebrows and sparked urgent discussions. Are these merely temporary anomalies, or are they early warnings of something far more significant? In this video, we'll dive deep into the fascinating yet controversial topic of whether we could realistically face a new ice age within our lifetime. You'll uncover groundbreaking scientific studies, startling predictions from climate experts, and real-world examples of recent cooling events that challenge the conventional wisdom about climate change. We'll explore how global warming, ironically, could potentially trigger a sudden cooling effect, a phenomenon that sounds contradictory at first glance but is supported by powerful scientific evidence. We'll examine the latest climate models and insights from experts who believe we're ignoring crucial signs pointing toward possible cooling. You'll also hear gripping stories from the past, historical case studies about societies dramatically impacted by previous ice ages, particularly the Little Ice Age. These stories not only paint a vivid picture of the human struggles involved but also offer critical lessons for how we might navigate a similar situation today. We'll ask tough questions. What would it mean for our modern world if temperatures suddenly plunged? How prepared are we to deal with the profound economic, agricultural, and humanitarian impacts? Could technology and innovation offer viable solutions, or are we dangerously unprepared? By the end of this video, you'll have gained a clear understanding of the reality behind Earth's climate future, backed by facts, statistics, expert insights, and controversial perspectives. You'll leave informed, curious, and equipped with knowledge about one of the most compelling questions facing humanity today: could we be on the brink of a new ice age? So settle in, keep an open mind, and let's begin this journey into the chilling truth about our planet's climate, and uncover whether the world as we know it might soon be facing dramatic, icy change. Understanding ice ages. A journey through Earth's frozen past. Ice ages are among the most transformative and dramatic events in Earth's climate history. They are long periods characterized by significantly colder global temperatures, during which vast ice sheets cover extensive areas of the planet. These massive ice formations reshape landscapes, influence ecosystems, and profoundly impact all forms of life, including humans. When did ice ages occur? Throughout Earth's 4.5 billion year history, scientists estimate the planet has experienced at least 5 major ice ages. Each ice age lasted millions of years and included alternating colder glacial periods, where ice sheets expanded extensively, and warmer interglacial periods, similar to the relatively temperate climate we currently enjoy. The earliest known ice age, the Huronian, occurred approximately 2.4 billion years ago and lasted for about 300 million years. During this time, Earth was almost entirely frozen, a condition often described by scientists as a snowball Earth. Later, the Cryogenian Ice Age, around 720 million to 635 million years ago, also plunged our planet into a deep freeze, significantly shaping early life forms. The most recent major ice age, the Quaternary, began approximately 2.6 million years ago and continues in cycles to this day. Although we're currently in a relatively warm interglacial period within this ice age, known as the Holocene epoch, Earth's climate has regularly shifted between warmth and extreme cold throughout these cycles. The last major glacial period peaked roughly 20,000 years ago, and massive ice sheets covered substantial parts of North America, Europe, and Asia. What triggered past ice ages? Scientists have identified several key factors contributing to past ice ages. Among the most critical are the Milankovitch cycles, named after Serbian astronomer Milutin Milankovic. These cycles describe slight variations in Earth's orbit and tilt, changing how much sunlight reaches the planet's surface. Over tens of thousands of years, these small orbital changes cause significant climate shifts, including the growth and retreat of ice sheets. Volcanic activity has also played a crucial role in triggering ice ages. Massive volcanic eruptions spew vast quantities of sulfur dioxide into the atmosphere, reflecting sunlight away from Earth and cooling the planet. A well-known example of volcanic influence occurred around 74,000 years ago with the eruption of Mount Toba in modern-day Indonesia. This eruption was so severe that scientists believe it may have dramatically cooled Earth's climate and even threatened human survival. Solar radiation fluctuations are another essential factor. Sunspots, dark, cooler areas appearing periodically on the sun's surface, indicate changes in solar output. Fewer sunspots mean less solar energy reaching Earth, contributing to global cooling. For example, scientists correlate the Little Ice Age, occurring between roughly 1300 and 1850 AD, with periods of significantly reduced sunspot activity. Why studying ice ages matters today? Understanding previous ice ages is vital because it provides scientists with essential insights into Earth's climate mechanisms and future climate predictions. By studying past ice ages, climate experts can develop more accurate predictive models and better understand potential future changes, including the possibility of rapid global cooling. Historical climate records, ice core samples, and geological evidence allow scientists to reconstruct past temperature variations, measure ice coverage, and analyze atmospheric compositions dating back hundreds of thousands of years. This evidence reveals critical climate data, such as how quickly temperatures dropped during past ice ages, the extent of glacial coverage, and the duration of colder periods. This data helps improve predictions for future climate behavior. Critical data and statistics of ice ages. The scale of change during ice ages is genuinely staggering. At the peak of the last glacial period, approximately 20,000 years ago, global temperatures averaged around 6 degrees Celsius, 10.8 degrees Fahrenheit, colder than today. This temperature drop might not sound dramatic, but it led to extensive ice sheets covering about 30% of Earth's land surface, compared to just 10% today. The ice sheets reached thicknesses of over 3 kilometers, 1.8 miles, in areas of North America and Europe, dramatically altering global sea levels by reducing them by approximately 120 meters, nearly 400 feet. These extensive ice sheets profoundly impacted life on Earth, forcing animals and human populations to migrate, adapt, or perish. Large mammals, such as woolly mammoths and saber-toothed tigers, roamed continents covered in ice, eventually becoming extinct as conditions changed rapidly with ice retreat. Human populations migrated across land bridges formed by lower sea levels, altering historical migration patterns and significantly influencing human evolution and cultural development. In total, ice ages significantly reshaped global ecosystems, ocean currents, and atmospheric patterns, leaving lasting impacts visible in modern geology, biology, and even human history. Studying these extensive changes gives scientists critical clues about how our planet responds to shifts in climate and what triggers massive environmental transformations. Today, scientists continue to analyze the delicate balance of natural cycles, volcanic activity, solar radiation changes, and human-induced climate effects. As we uncover more about the past, it becomes increasingly vital to ask ourselves whether our current climate stability could be disrupted again, perhaps sooner than we think. As we continue this exploration into Earth's climate future, we'll examine whether current trends could hint at the onset of a new ice age, dramatically altering our understanding of global climate change. The Little Ice Age, when the world suddenly turned cold. The phrase ice age often conjures images of massive glaciers covering continents tens of thousands of years ago, but few realize that humanity experienced a more recent chilling event known as the Little Ice Age. Occurring between approximately 1300 and 1850 AD, this dramatic cooling period profoundly affected societies worldwide, reshaping history in ways many don't fully understand. A sudden shift in Earth's climate. The Little Ice Age wasn't as extreme as previous full-scale ice ages, yet its impacts were severe and widespread. Beginning around the early 14th century, temperatures across much of Europe, North America, and parts of Asia dropped significantly, with some regions experiencing average temperature decreases of approximately 1 to 2 degrees Celsius, 1.8 to 3.6 degrees Fahrenheit. This seemingly small drop was enough to dramatically shorten growing seasons, expand glaciers, and freeze rivers and lakes that previously rarely experienced ice. Historical records from Europe describe prolonged winters, intense snowfall, and summers so cold and wet that crops failed repeatedly. In London, the Thames River froze so thoroughly that residents held festivals called frost fairs, building markets, skating rinks, and even entire temporary villages atop the thick ice. Yet beneath this seemingly picturesque scene was a harsh reality of widespread hardship, famine, and economic collapse. How the Little Ice Age changed humanity. As temperatures plummeted, societies struggled desperately to adapt. Agriculture, the cornerstone of medieval economies, was devastated by shorter, cooler growing seasons. Crops failed frequently, leading to repeated famines throughout Europe and parts of Asia. One of the most devastating was the Great Famine from 1315 to 1317, when heavy rains destroyed harvests and caused mass starvation. Historical records estimate that up to 15% of Northern Europe's population perished during this crisis alone. Beyond famines, the Little Ice Age intensified the spread of disease. Colder temperatures weakened immune systems due to malnutrition, making populations more vulnerable. In fact, historians and epidemiologists connect these harsh climatic conditions with the severity of disease outbreaks, including the catastrophic spread of the Black Death in the mid-14th century, which wiped out nearly one-third of Europe's population. Economically, the Little Ice Age had devastating consequences. Failed harvests pushed grain prices to record highs, causing widespread poverty and triggering riots. Fishing communities suffered as fish populations migrated to warmer waters or deeper oceans, drastically altering local economies dependent on the sea. Trade routes became blocked by ice, disrupting commerce and isolating regions dependent on imported food and supplies. Scientific theories behind the Little Ice Age. Scientists have studied the Little Ice Age extensively, trying to understand precisely what caused this abrupt climatic shift. Today, two leading theories dominate discussions. The first theory involves reduced solar activity, often associated with sunspots. Sunspots are cooler, darker regions appearing periodically on the sun's surface. A significant reduction in sunspot activity, known as the Maunder minimum, occurred between 1645 and 1715. During this 70-year span, scientists observed almost no sunspots, indicating that less solar radiation reached Earth. This reduction in solar energy likely contributed significantly to global cooling. The second prominent theory revolves around volcanic eruptions. Massive eruptions release enormous amounts of ash and sulfur dioxide into Earth's atmosphere, creating an aerosol veil that blocks sunlight, resulting in cooling. Several major volcanic eruptions during this period, including the eruption of Mount Tambora in 1815, intensified cooling dramatically. Tambora's eruption alone caused what became known as the Year Without a Summer in 1816. Crops failed worldwide, even in typically temperate regions, leading to widespread starvation and economic disruption. The data and statistics behind the Little Ice Age wasn't uniformly cold, but temperature reconstructions from ice core data and historical documents confirm that it was consistently cooler than preceding and following periods. Average global temperatures during this time were roughly 1.0 to 1.5 degrees Celsius lower than today's temperatures. While this may seem minor, even such small global temperature changes severely impacted growing seasons, agricultural productivity, and human survival. In Europe, shorter summers led to reduced harvests by as much as 30% compared to warmer periods. Historical documents detail numerous years of complete agricultural collapse, particularly from 1600 to 1700, when weather extremes became more frequent. Europe's population growth stagnated, with historians attributing approximately 10 to 20% of excess mortality during peak famine years directly to climate-induced food shortages and disease outbreaks. In Asia, particularly in China, similar climatic hardships occurred. Historical records from the Ming dynasty note severe droughts and freezing winters in northern China, causing mass migrations, widespread famine, and social upheaval, eventually contributing to dynastic collapse. Overall, the Little Ice Age vividly demonstrates how even modest global cooling can profoundly disrupt human societies. By examining this recent climate event, scientists gain critical insights into how humanity might respond to future cooling episodes. These lessons underscore the importance of understanding whether such climatic events could recur within our lifetime, dramatically reshaping our modern, interconnected world. As we move forward in this exploration, we'll closely examine signs and evidence suggesting our planet could again face significant cooling, potentially leading toward conditions reminiscent of the Little Ice Age or even more extreme events in our near future. Is global warming masking the early signs of an ice age? When we think of climate change, we typically picture rising temperatures, melting ice caps, and scorching heat waves. But recently, scientists have started raising a surprising and controversial question. Could global warming actually be hiding early signs of significant global cooling? This idea may sound counterintuitive at first. After all, how could warming mask cooling? However, Earth's climate is incredibly complex, driven by interconnected systems and delicate balances. Historically, dramatic shifts from warm to cold conditions have happened rapidly, often catching humanity by surprise. Strange cold snaps and unexpected snowfalls in recent years have brought a series of baffling weather anomalies across the globe, making scientists rethink conventional wisdom. For example, in February 2021, a historic winter storm swept through Texas, a state famous for its mild winters. Millions of people were left without power, struggling to cope with record low temperatures. In some parts, temperatures plunged to -19 degrees Celsius, -2 degrees Fahrenheit, shattering century-old records. Even places known for scorching heat aren't immune to sudden cold snaps. In January 2018, the Sahara Desert, the hottest desert on Earth, experienced a rare snowfall, blanketing sand dunes with a surreal layer of snow. Similarly, in the Middle East, regions typically associated with extreme heat have recently endured record-breaking cold. Saudi Arabia witnessed heavy snowfalls multiple times over the past decade, leaving locals astonished as deserts transformed overnight. Europe and Asia, unexpected deep freezes. Europe hasn't escaped these anomalies either. During the winter of 2018, Europe was hit by what meteorologists call the beast from the east. Arctic air surged into the continent, causing temperatures to plunge far below average. Countries like the United Kingdom, Germany, and Poland recorded some of their coldest temperatures in decades. Airports closed, public transport halted, and thousands suffered through intense cold conditions that lasted far longer than typical winter cold spells. Across Asia, similar events have unfolded. In December 2022, Japan experienced record-breaking snowfall, with over 2 meters, about 6 feet, falling within just a few days. This event disrupted transportation, isolated communities, and forced emergency services to conduct daring rescues. China, too, has faced unusual winter weather in recent years, with Beijing recording its coldest temperatures in half a century during January 2021. What's behind these sudden cold spells? These strange weather patterns have reignited discussions among climate scientists. Some argue that such anomalies are merely short-term fluctuations, temporary irregularities in an otherwise warming world. But others contend these events could represent early warnings of something far more significant, potential shifts in global climate dynamics indicating possible cooling trends beneath the surface of current warming. One prominent theory gaining attention is related to the weakening of the Atlantic Meridional Overturning Circulation, AMOC, a major ocean current system that distributes heat globally. Recent scientific studies indicate the AMOC is slowing down significantly. A weakened AMOC means less warm water moves northward from the tropics, potentially plunging parts of North America and Europe into colder conditions. According to a study published in the journal Nature in 2021, the AMOC's strength is currently at its weakest in over 1,000 years. Polar ice variations and ocean anomalies. Further evidence comes from unexpected polar ice variations. While we constantly hear about shrinking Arctic ice, scientists have observed curious patterns in Antarctic sea ice. Over the past decade, Antarctic ice extent has experienced surprising fluctuations, with some years showing increases well above historical averages. For instance, in 2014, Antarctic sea ice reached record-breaking extents, expanding to approximately 20 million square kilometers, 7.72 million square miles, the highest recorded level since satellite monitoring began in the late 1970s. Ocean temperatures are also providing intriguing clues. Deep sea temperature measurements indicate colder water masses accumulating in parts of the Atlantic and Southern Oceans. Scientists studying these patterns suggest such anomalies might signal significant shifts in ocean currents, potentially leading to abrupt regional cooling events. Could we really be heading toward a new ice age? Climate scientists acknowledge that predicting Earth's climate future remains a monumental challenge. Yet, historical records show that abrupt cooling events have happened repeatedly, sometimes triggered by subtle changes. The Little Ice Age is a prime example of how slight changes in solar radiation, volcanic activity, or ocean currents can plunge large portions of Earth into colder climates within decades. Today's unusual cold snaps and unexpected climate anomalies might just be temporary disturbances. Yet, their frequency and intensity are causing concern. Prominent climate experts have begun openly discussing the controversial possibility that we might be underestimating our climate's vulnerability to rapid cooling. Dr. Valentina Zharkova, a respected solar physicist, has notably proposed that decreased solar activity over the next several decades could lead to significant global cooling. Her predictions, based on solar magnetic cycle patterns, suggest Earth could experience another cooling phase similar to the Maunder minimum during the Little Ice Age. This viewpoint remains controversial, with vigorous debates within the scientific community. However, the increasing number of unexpected cold events, coupled with ocean current disruptions and polar ice variations, underscores the need for deeper investigation into global cooling scenarios. Preparing for uncertain climate shift. Whether or not these events signal an approaching ice age remains uncertain, but one thing is clear: Earth's climate is complex, dynamic, and sometimes unpredictable. Climate models are continually evolving, and scientists are rapidly gathering new data to understand precisely what these anomalies signify for our planet's future. As we continue exploring Earth's climate future in this video, we'll examine how global warming itself might paradoxically lead to rapid cooling by disrupting vital ocean currents and climate systems. We'll also investigate how prepared we really are if significant cooling occurs, potentially reshaping our understanding of climate change altogether. Ultimately, recognizing and analyzing these emerging cooling trends doesn't diminish the urgency of addressing global warming. Instead, it broadens our understanding, reminding us that Earth's climate might hold surprises that conventional wisdom hasn't fully accounted for. This deeper understanding can help humanity better anticipate and adapt to whatever climatic challenges lie ahead. With climate anomalies becoming more frequent, and new scientific evidence emerging, we must remain vigilant. Could these seemingly isolated cold events be early indicators of a much colder future ahead? Let's continue this exploration and uncover what scientists are truly discovering about Earth's rapidly changing climate. Could global warming actually trigger an ice age? At first glance, the idea seems contradictory. How could global warming, the steady rise of Earth's average temperatures, actually set off a rapid cooling event, potentially triggering a new ice age? Yet, scientific research and climate models indicate that our warming world might indeed face this paradoxical and alarming scenario. Understanding how warming could lead to cooling requires a closer look at Earth's delicate climate mechanisms, particularly our planet's complex ocean currents. Earth's ocean currents, the climate's hidden engine. Earth's oceans play an essential role in regulating global climate by absorbing, storing, and redistributing heat around the planet. Central to this process is the Atlantic Meridional Overturning Circulation, known simply as the AMOC. Often described as a giant conveyor belt, the AMOC moves warm surface waters from tropical regions northward into the North Atlantic. When these waters reach higher latitudes near Greenland and the Arctic, they cool, become denser, and sink deep below the ocean surface, traveling back south as cold, deep currents. This constant flow of warm and cold water stabilizes temperatures, especially in regions like Europe and North America. Without this circulation, northern Europe would experience climates similar to those in Siberia or northern Canada, vastly colder and less hospitable. How melting ice caps can halt the ocean conveyor belt. Global warming is causing massive ice sheets and glaciers in Greenland and the Arctic to melt at unprecedented rates. Greenland alone has lost an estimated 280 billion tons of ice per year since the early 2000s, according to NASA satellite measurements. This enormous influx of freshwater into the North Atlantic disrupts the AMOC because freshwater is lighter than salty ocean water, meaning it doesn't sink easily. As freshwater accumulates, it interferes with the ocean's ability to push warm surface water downward, weakening the conveyor belt. Recent studies indicate that the AMOC is already experiencing noticeable weakening. Research published in the journal Nature Geoscience in 2021 revealed that the circulation is at its slowest pace in more than 1,600 years, driven primarily by melting Arctic ice and increased freshwater runoff. This slowdown could set the stage for a more drastic cooling event if conditions worsen. Historical lessons: warming followed by sudden cooling. Historical records and climate data support the idea that rapid cooling events have happened before after warming periods. Around 12,800 years ago, Earth experienced a dramatic cooling episode known as the Younger Dryas, during which temperatures in the northern hemisphere plummeted by approximately 5 to 10 degrees Celsius, 9 to 18 degrees Fahrenheit, in just a few decades. Scientists believe that this sudden shift resulted from freshwater flooding into the North Atlantic, halting the AMOC and plunging regions into an intense cold phase lasting roughly 1,200 years. This historical precedent offers a crucial warning about our present-day climate trajectory. If current melting trends continue unchecked, scientists warn, we might risk recreating conditions that once triggered rapid global cooling. Although the exact timing remains uncertain, recent climate models suggest that continued warming and ice melting could dangerously destabilize ocean circulation within the next century, possibly even within decades. What climate models and scientists predict today? Leading climate scientists and research organizations have used sophisticated computer models to simulate the potential impacts of AMOC disruption. According to a groundbreaking report published in Nature Communications in 2022, climate modeling indicates a 50% likelihood that the AMOC could collapse or drastically slow down by the year 2100 if global warming remains unchecked. Such a collapse would significantly cool northern hemisphere climates, affecting weather patterns worldwide. Another study conducted by scientists from the Potsdam Institute for Climate Impact Research in Germany suggests an even more urgent scenario. They concluded that the AMOC is already dangerously close to a critical tipping point. If crossed, this point could trigger rapid and irreversible cooling within mere decades, dramatically reshaping global climates and ecosystems. However, not all scientists agree on how imminent or severe this risk is. Many climate experts argue that current models cannot precisely predict tipping points, urging caution against overstating immediate threats. While there's consensus that the AMOC is weakening, debates continue regarding precisely when or if it might collapse entirely. The controversy and debates among climate scientists. Despite accumulating evidence, the debate among climate scientists remains intense. Some argue that the idea of global warming leading to significant cooling scenarios remains speculative, lacking sufficient observational evidence. They point to the complexity of climate systems and argue that while AMOC slowdown is happening, it might not lead to a full collapse. Others strongly disagree, insisting that the evidence of AMOC weakening is already compelling enough to demand urgent global attention. They emphasize the need to integrate ocean current data into global climate strategies immediately. These scientists warn that ignoring the potential for rapid cooling could leave societies dangerously unprepared for abrupt climate shifts. Prominent climatologist Dr. Stefan Rahmstorf, a leading researcher studying AMOC changes, has been vocal about the real risk posed by its weakening. Rahmstorf stresses that while exact predictions are challenging, the clear evidence of significant AMOC slowdown should serve as a wake-up call for policymakers and society to act swiftly, considering both warming and potential cooling scenarios in climate planning. Preparing for the unexpected. What if rapid cooling occurs? Should significant cooling events unfold, the consequences would be dramatic. Agricultural systems, infrastructure, and economies across North America and Europe could face severe disruption. Northern Europe could see significantly shorter growing seasons, widespread agricultural failures, and increased energy demands for heating, mirroring conditions historically seen during the Little Ice Age. To prepare adequately, scientists argue that it's crucial to include cooling scenarios in climate resilience plans. Nations must consider investments in food security, infrastructure adaptability, and renewable energy solutions capable of withstanding severe weather extremes, whether from heating or cooling. Ignoring the potential for abrupt cooling could leave entire regions dangerously vulnerable. In conclusion, the paradox of global warming triggering rapid cooling is increasingly supported by robust scientific research and historical precedents. While uncertainties remain, the AMOC's ongoing weakening and historical examples demonstrate the potential severity of abrupt climate shifts. Understanding and preparing for these scenarios is essential, not just for scientists, but for all of humanity, as we navigate an uncertain climate future. In the next section, we'll explore in detail what climate models are predicting about Earth's future climate and how scientists are preparing to address potential global cooling risks. Climate models, predicting Earth's uncertain future. Climate models are powerful tools scientists use to understand Earth's complex climate system and anticipate future changes. These sophisticated computer simulations analyze enormous datasets, from ocean temperatures to atmospheric conditions, providing critical predictions about how our planet's climate might evolve. As global temperatures rise, some surprising predictions have emerged, including scenarios that suggest our warming world could trigger sudden, dramatic cooling events, potentially even leading toward another ice age. Latest climate model predictions. What do they reveal? In recent years, several advanced climate modeling studies have sounded alarms about potential cooling scenarios, particularly relating to the Atlantic Meridional Overturning Circulation, AMOC. A groundbreaking study published in Nature Communications in 2022 used detailed simulations to investigate how rapidly the AMOC might weaken in response to current global warming trends. Researchers discovered a troubling 50% probability that the AMOC could drastically slow or even collapse entirely before the end of this century if greenhouse gas emissions aren't significantly reduced. Another prominent climate model developed by researchers at the Potsdam Institute for Climate Impact Research produced even more startling predictions. According to their findings, the AMOC may be dangerously close to a tipping point already. Crossing this critical threshold could trigger rapid climate cooling across North America and Europe within mere decades, not centuries. Such rapid shifts would significantly impact agriculture, ecosystems, and human populations across these densely populated regions. These models, though not guaranteeing outcomes, provide crucial warnings that abrupt climate shifts are scientifically plausible, and potentially imminent if current emission trajectories continue unchecked. Global cooling scenarios, insights from recent studies. Several studies have specifically explored scenarios in which global warming paradoxically leads to cooling events. A study published in Science Advances in 2021 highlighted how freshwater influx from melting Arctic and Greenland ice could significantly disrupt ocean currents. This disruption, researchers warned, might produce regional cooling events similar in scale to those experienced during historical cold periods such as the Little Ice Age. Another influential analysis appeared in the Journal of Climate in 2020, demonstrating through detailed climate models that AMOC weakening could reduce average winter temperatures across northern Europe by up to 4 degrees Celsius, 7.2 degrees Fahrenheit. While this decrease might sound modest, scientists emphasized that such a shift could shorten growing seasons dramatically, causing frequent agricultural failures and increasing energy demands for heating, leading to severe socio-economic disruptions. Leading scientists speak out, perspectives and insights. Climate scientists worldwide have increasingly expressed concern about the possibility of rapid cooling events linked to AMOC instability. Dr. Stefan Rahmstorf, a prominent climatologist at the Potsdam Institute, has consistently highlighted the risk, noting that climate models clearly indicate AMOC weakening as a substantial threat. Rahmstorf emphasizes that even partial disruption of the AMOC could significantly cool parts of Europe, triggering climate-related challenges societies aren't prepared for. Another influential voice is Dr. James Hansen, former NASA scientist and a leading climate expert. Hansen warns that conventional discussions about climate change often underestimate abrupt climate shifts. He stresses the importance of preparing for rapid, unexpected cooling events that historical records clearly demonstrate are possible. Dr. Valentina Zharkova, a respected solar physicist from Northumbria University, offers a different but related perspective. Her controversial research predicts a decrease in solar activity over the coming decades, possibly triggering significant cooling reminiscent of the Little Ice Age. Although Zharkova's predictions have stirred debate, they highlight an essential consideration, that factors beyond human-driven warming, like solar activity, might play critical roles in our climate future. Debates and controversies. Is an ice age scenario realistic? Despite these compelling models and studies, debates continue within the scientific community regarding how likely and how imminent a global cooling scenario might be. Many climate experts caution against overstating the risks, arguing that while AMOC weakening is real and measurable, predicting exact tipping points remains extremely challenging. They advocate focusing primarily on global warming as the immediate threat, suggesting that rapid cooling remains speculative and less immediately pressing. Other scientists, however, maintain that this cautious approach might lead society to underestimate significant risks. They argue that historical precedents, like the Younger Dryas and Little Ice Age events, clearly demonstrate Earth's climate is prone to abrupt changes triggered by seemingly subtle shifts in ocean circulation or solar radiation. Ignoring these possibilities, they suggest, could leave societies dangerously unprepared for sudden climate shocks. Critical statistics and scientific predictions. Recent scientific predictions underscore the seriousness of these cooling scenarios. The Intergovernmental Panel on Climate Change, IPCC, the world's leading climate assessment organization, has increasingly recognized AMOC weakening as a critical climate risk. The IPCC's sixth assessment report, released in 2021, acknowledged that a significant weakening or collapse of the AMOC before 2100 is plausible under scenarios of continued high emissions, carrying a medium confidence rating, indicating substantial scientific agreement, though uncertainty remains. Quantitative predictions from climate models emphasize potential impacts clearly. According to modeling conducted at the Potsdam Institute, a sudden AMOC collapse could lead to rapid regional cooling, potentially reducing northern European winter temperatures by as much as 5 degrees Celsius, 9 degrees Fahrenheit, within just a few decades. Such a scenario would dramatically alter growing seasons, agricultural productivity, and energy demand patterns, profoundly reshaping economic and societal stability. Other models indicate severe climatic disruptions in North America, particularly along the eastern seaboard, where major cities like New York, Boston, and Montreal could experience significantly harsher winters. Simulations suggest snowier, colder winters and shorter summers, disrupting transport, commerce, and food production. These statistics make it clear that the stakes involved are substantial. While exact outcomes remain uncertain, the mere possibility of rapid cooling necessitates serious consideration in climate planning and policy. Preparing for an uncertain climate future. Ultimately, the diverse predictions offered by climate models highlight a crucial reality: Earth's climate is complex, unpredictable, and vulnerable to rapid shifts. Global warming remains a pressing issue requiring urgent action, but understanding the full range of climate risks, including abrupt cooling scenarios, is equally critical. By embracing this comprehensive perspective, humanity can better prepare for whatever the future might hold, ensuring resilience in the face of uncertainty. As we continue exploring the possibility of another ice age, we'll delve deeper into what such an event could mean for humanity today. From agricultural disruptions to economic upheaval, the consequences of rapid cooling could be profound, reminding us of the urgency in understanding Earth's fragile climate balance. How would a modern ice age transform our world? If a new ice age were to occur in our modern, interconnected world, its impacts would be dramatic, wide-ranging, and potentially catastrophic. Unlike ancient societies, today's global civilization is highly interdependent, making us more vulnerable to sudden disruptions. From agriculture and trade to population movements and refugee crises, the consequences of a significant cooling event would reshape life on Earth in profound ways. Agriculture in crisis, feeding the world amid the freeze. Agriculture is the backbone of civilization, providing food, employment, and economic stability worldwide. A rapid cooling scenario, even moderate in intensity, would drastically affect global food production. Crops we rely upon today, such as wheat, rice, corn, and soybeans, require specific temperature ranges and predictable growing seasons. Sudden temperature declines, like those projected in severe cooling models, would significantly shorten growing seasons, triggering widespread agricultural failures. Historical records illustrate the severity of this threat clearly. During Europe's Little Ice Age, just a 1 to 2 degrees Celsius temperature drop led to harvest reductions of 20%–30% in many regions. Today, similar or larger declines in global yields would result in widespread food shortages, skyrocketing food prices, and mass hunger, particularly affecting vulnerable regions that rely heavily on imported foods. Regions like North America, Europe, Russia, and northern China, currently major global grain producers, would face substantial decreases in crop yields. Studies modeling moderate climate cooling predict up to a 40% decline in global grain production. Such reductions could leave billions facing food insecurity, reversing decades of progress in combating global hunger. Economic disruption, the global economy at risk. Beyond food production, a new ice age would trigger economic disruptions on a massive scale. Global supply chains, already sensitive to minor shocks, would face severe disruptions as trade routes become unstable. Ports could freeze over, particularly in regions unused to sustained cold, causing shipping delays, rising transportation costs, and shortages of essential goods. The direct economic impact on agriculture alone would be staggering. Agriculture contributes over $5 trillion annually to the global economy and employs over 1 billion people. A sudden and sustained reduction in agricultural productivity could cause GDP losses exceeding hundreds of billions annually, possibly reaching trillions over a prolonged period. Such losses would not only devastate farming communities but also significantly affect related industries like transportation, manufacturing, and retail. Additionally, energy demands would skyrocket as populations require more heating. This would put intense pressure on existing energy grids, driving prices higher and causing widespread fuel shortages. Historical data from severe winters shows energy demands often increase by 20% to 40%, and extended cold periods would intensify these impacts dramatically. Countries dependent on energy imports could experience economic shocks, human migration, and the emergence of climate refugees. One of the most significant societal impacts of a modern ice age would be mass human migration. Historically, humans adapted to climate shifts by moving toward warmer, more habitable regions. Today, with densely populated cities and established national borders, mass migration becomes an even more complex and disruptive issue. Severe cooling in northern latitudes, particularly Europe, North America, and parts of Asia, would likely push tens or even hundreds of millions to migrate southward toward more temperate zones. This unprecedented movement could trigger major refugee crises, dwarfing recent migration events seen due to conflicts or economic hardship. For example, a comprehensive simulation conducted by climate researchers indicated that a sudden 3 to 5 degrees Celsius drop in average northern hemisphere temperatures could displace between 300 to 500 million people globally. Such a mass movement would overwhelm current immigration systems, leading to severe humanitarian crises, political instability, and potential conflicts over resources and territory. Lessons from history: understanding the human cost of cooling. Historical cooling periods like the Little Ice Age provide valuable insights into what might unfold during significant global cooling. During Europe's Great Famine, 1315 to 1317, crop failures caused by unusually cold and wet weather led to starvation and social collapse, reducing populations in some regions by as much as 15% to 20%. Economic disruptions followed, as local economies and trade collapsed under sustained agricultural failure. Moreover, famines and resource scarcity increased social unrest, violence, and war. Historical documents reveal spikes in conflict, rebellions, and societal breakdowns closely associated with climate-induced resource scarcity during cooling periods. Today, with a much larger global population of over 8 billion people, similar scenarios would have exponentially greater consequences. Even moderate disruptions in global food production, combined with mass migrations, could escalate quickly into geopolitical conflicts and widespread instability. Quantifying the impacts, GDP loss, agricultural failures, and displacement. Recent climate economic modeling provides clear estimates of potential impacts from rapid cooling scenarios. According to simulations published by leading economic and climate research organizations, moderate global cooling could cause cumulative GDP losses of more than 10%, 15% globally within a decade. More severe scenarios suggest even larger economic impacts, potentially exceeding 20% GDP losses for major economies reliant on agriculture, trade, and stable energy supplies. For context, global GDP currently exceeds $100 trillion annually. A sustained economic contraction of 10%, 20% translates to tens of trillions of dollars lost, significantly surpassing economic disruptions experienced during major events like the global financial crisis of 2008. Population displacement figures would be equally severe. Climate models forecasting significant cooling predict hundreds of millions of displaced individuals globally. Europe alone could experience over 50 million internal migrants within the first decade of sustained cooling, with similar numbers expected in North America and Asia. Agricultural failures would rapidly multiply these challenges. Global grain reserves today typically cover only a few months of consumption. Persistent reductions in harvests would quickly deplete these reserves, triggering shortages, price spikes, and widespread hunger. Nations heavily reliant on food imports, particularly in Africa, the Middle East, and parts of Asia, could face catastrophic famines within just a few years of disrupted global agricultural production. Preparing for the unthinkable. Although the likelihood of another ice age within our lifetime remains debated, the potential consequences of significant global cooling highlight an urgent need for preparedness. Climate resilience strategies must now consider not just warming scenarios, but also the plausible, if less intuitive, threat of rapid cooling events. By examining historical lessons, current climate data, and robust economic modeling, we understand the profound impacts another ice age could have on humanity today. Recognizing these risks can help societies better anticipate and prepare for the immense challenges posed by sudden climatic shifts, ensuring we are not caught off guard by one of Earth's most dramatic natural phenomena. In our next section, we will explore whether technology and innovation might help humanity navigate through such unprecedented global climate challenges, potentially providing solutions, or at least strategies, to survive a modern ice age. Can technology protect humanity from a new ice age? As scientists increasingly warn about potential rapid cooling events or even a modern-day ice age scenario, attention has shifted toward technology as our best hope for mitigation. With unprecedented advances in science and engineering, many wonder if humanity is now technologically equipped to adapt to, or even prevent, such catastrophic climate disruptions. But how ready are we, really? Technological readiness. Are we prepared? Today's technology vastly surpasses what previous generations had at their disposal, making us better equipped in some ways to withstand extreme climate shifts. Agricultural innovations, energy-efficient infrastructure, renewable energy systems, and sophisticated climate modeling give humanity powerful tools for adaptation. Yet, despite these strengths, our global civilization remains vulnerable due to limited preparations for sudden cooling scenarios. Agricultural technologies provide a striking example. While modern farming techniques have increased yields and crop resilience in warmer climates, adapting quickly to colder conditions remains a significant challenge. Greenhouses, indoor farming, and hydroponics offer promising solutions, allowing food production in controlled environments unaffected by external temperatures. Countries like the Netherlands already demonstrate success in large-scale greenhouse farming, achieving high yields even in colder climates. Scaling these technologies globally, however, remains expensive and complex, making them viable mainly in wealthier nations. Innovative ideas to mitigate global cooling. Scientists and engineers are exploring innovative technologies explicitly designed to counteract rapid cooling effects. One promising area is genetic engineering of crops to improve cold tolerance and shorten maturation cycles. Researchers at agricultural biotechnology firms have successfully developed crop strains capable of growing faster and resisting frost damage. Although still limited in commercial application, these genetically modified crops could provide critical food sources if global temperatures drop significantly. Energy infrastructure adaptation is another vital technological frontier. Renewable energy sources like solar and wind power can still operate in colder climates, provided infrastructure is properly winterized. Advances in battery storage technologies also make it possible to store energy generated during periods of favorable weather, ensuring continuous supply even during prolonged cold periods. Scandinavian countries, particularly Sweden and Denmark, already implement extensive winterized renewable energy grids, providing valuable case studies for global adaptation. Geoengineering, controversial solutions and their feasibility. Perhaps the most controversial technologies proposed to mitigate severe climate events fall under the category of geoengineering. Geoengineering involves large-scale interventions designed to manipulate Earth's climate deliberately. While most geoengineering proposals focus on cooling a warming planet, some methods could theoretically be adapted to address global cooling scenarios. One particularly controversial idea involves solar shields or space-based mirrors designed to reflect additional sunlight toward Earth's surface to compensate for reduced temperatures. Although this concept may sound like science fiction, researchers at institutions such as Harvard and MIT have seriously explored solar reflection technologies. Despite promising theoretical models, the immense cost, technological complexity, and potential unintended consequences make solar shields highly controversial. Many climate scientists warn that manipulating Earth's delicate climate balance could create unpredictable side effects, possibly worsening the situation. Another proposed geoengineering approach involves artificially managing ocean currents to stabilize global temperatures. Scientists suggest methods such as underwater barriers or artificial pumping stations that enhance warm water flow, preventing the AMOC from collapsing. However, these solutions remain highly experimental, technically challenging, and potentially risky, given the complexity of ocean systems. Real-world case studies, nations preparing for climate extremes. Certain countries and companies have already started investing in technologies that could mitigate the impacts of sudden climate shifts. Iceland provides an illustrative example. The country harnesses geothermal energy extensively, ensuring stable energy production regardless of external temperatures. Icelandic greenhouses powered by geothermal heat already produce substantial portions of the country's vegetables, making Iceland uniquely prepared for potential global cooling events. In North America, Canada has proactively funded research into agricultural resilience, including development of crops genetically engineered for colder climates and indoor farming technologies. Companies like AeroFarms and Plenty have invested heavily in indoor vertical farming, demonstrating the feasibility of large-scale food production independent of outdoor climate conditions. These innovations position them as global leaders in agricultural adaptation, potentially serving as critical resources if significant cooling occurs. Norway offers another valuable case study, showcasing sophisticated renewable energy and robust infrastructure adapted for harsh winter conditions. Extensive investment in renewable energy infrastructure, including hydroelectric power and wind farms built to withstand severe cold, has significantly increased Norway's resilience against temperature extremes. Can technology alone save us? While these technological advances offer real hope, relying solely on technology to mitigate the impacts of a sudden global cooling event remains risky. Innovative agricultural practices, renewable energy solutions, and geoengineering proposals each come with considerable limitations, uncertainties, and costs. Additionally, scaling these technologies globally to reach vulnerable populations in poorer regions presents enormous logistical and financial challenges. Experts widely agree that while technology plays a critical role, comprehensive climate preparedness must also involve political action, international collaboration, and robust social planning. Technology can certainly help humanity adapt, but it cannot fully eliminate the risks posed by an abrupt climate shift. In our next section, we'll explore how leading climate experts and researchers view the possibility of rapid cooling events, discussing controversial insights, debates, and the complexity surrounding our current understanding of Earth's climate future. By examining these expert perspectives, we'll gain a clearer picture of what science truly tells us about the likelihood of facing another ice age in our lifetime. What do experts really think about a new ice age? In discussions about the possibility of Earth entering another ice age, expert opinions vary dramatically, reflecting the complexity and uncertainty surrounding our climate's future. Climate scientists, economists, historians, and even climate skeptics each offer distinct insights, creating lively debates that highlight how unsettled the science behind rapid cooling scenarios remains. Climate scientists themselves differ greatly in their assessments. Dr. Stefan Rahmstorff, a leading climatologist at the Potsdam Institute, strongly emphasizes the risks associated with the weakening of the Atlantic Meridional overturning circulation, AMOC. According to Rahmstorff, recent data clearly shows significant AMOC weakening, and he argues that society must urgently consider the potential for rapid cooling events. Rahmstift's perspective, widely respected in scientific circles, has pushed this previously obscure issue into mainstream climate discussions. Contrasting Rahmstift's cautious warnings, Dr. Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, advises against alarmism regarding rapid cooling. Schmidt maintains that while AMOC weakening is a real concern, current scientific models still involve substantial uncertainties. He urges policymakers to focus primarily on the immediate, measurable impacts of global warming, like rising sea levels and increasing temperatures, rather than speculative cooling scenarios. Schmidt's pragmatic approach represents a substantial portion of the scientific community that cautions against diverting resources away from addressing global warming directly. Historians add valuable perspectives by highlighting humanity's experience with past cooling periods. Dr. Jeffrey Parker, a renowned historian specializing in climatic impacts on human civilization, emphasizes that even modest cooling has historically caused severe societal disruption. His detailed studies of the 17th century Little Ice Age show that temperature drops of just 1 to 2 degrees Celsius triggered devastating famines, economic collapse, and social unrest. Parker argues that our modern, globally connected world might be even more vulnerable, urging society to prepare more proactively for potential climate disruptions, whether warming or cooling. Economists are increasingly examining the financial implications of abrupt climate shifts. Dr. Nicholas Stern, former chief economist at the World Bank and author of the influential Stern Review on Climate Change Economics, stresses the economic risks posed by sudden, unexpected climate changes. While Stern's primary focus remains on global warming, he acknowledges that abrupt cooling events, if they occurred, could lead to unprecedented economic disruptions. Stern advocates for comprehensive climate resilience investments that consider multiple scenarios, including rapid cooling, to prevent severe economic instability. Climate skeptics and controversial figures further complicate the discussion, often presenting views sharply critical of mainstream climate science. One of the most prominent skeptics, Dr. Bjorn Lomborg, director of the Copenhagen Consensus Center, argues that fears about a new ice age are significantly overstated. Lomborg emphasizes economic adaptation as humanity's primary strength, insisting that any cooling scenario, should it occur, would likely be manageable due to technological advancements and human innovation. His optimistic perspective sharply contrasts with those warning about potential catastrophe, creating heated debate among policymakers and the public. Perhaps the most controversial voice is Dr. Valentina Zharkova, a solar physicist from Northumbria University. Zharkova gained international attention for her research predicting significant global cooling based on solar cycles. Her work forecasts a period of reduced solar activity over the next several decades, potentially mirroring conditions experienced during the Little Ice Age. Zharkova's predictions remain highly contentious within the scientific community. Critics point out that linking solar cycles directly to severe cooling lacks robust empirical support. Yet, her provocative views resonate strongly in public debates, illustrating how polarizing the topic of global cooling remains. These diverse perspectives demonstrate the complexity and nuance inherent in climate predictions. Despite significant advances in climate modeling, substantial uncertainties persist, leading to ongoing disagreements among respected experts. the current scientific consensus clearly acknowledges global warming as the primary immediate threat. However, the question of whether warming could paradoxically trigger abrupt cooling remains open-ended, fueling passionate debates within and beyond the scientific community. Ultimately, examining these varied expert insights provides a balanced, factual overview without advocating for any single viewpoint. Recognizing the diversity of expert opinions allows policymakers, researchers, and the public to better understand the real uncertainties involved, encouraging cautious, informed planning for any potential climatic scenario, warming or cooling. As we continue our exploration, we'll next address some common misconceptions about ice ages, clarifying myths and misinformation that often cloud public understanding. By separating fact from fiction, we'll further deepen our comprehension of Earth's complex and ever-changing climate history. Common misconceptions about ice ages. Separating fact from fiction. When discussing ice ages, numerous myths and misconceptions often cloud public understanding. One widespread misunderstanding is that an ice age would mean a uniformly frozen Earth. In reality, during previous ice ages, glaciers covered only about 30% of Earth's surface, not the entire planet. Many regions remained ice-free, though colder. Another common misconception is that ice ages happen overnight or within a few years. While sudden cooling events can occur relatively quickly, full-scale ice ages typically unfold over hundreds or thousands of years. Historical records and geological data clearly demonstrate these processes take considerable time, giving humanity some opportunity, though limited, to adapt. Social media frequently circulates myths suggesting global warming has completely prevented future ice ages. While increased carbon dioxide levels indeed warm the planet, scientists caution that warming could paradoxically trigger rapid cooling if ocean currents are disrupted. Recent scientific studies clearly indicate that global warming does not guarantee protection from future cooling scenarios. Finally, popular culture often portrays ice ages as permanent or irreversible once started. However, Earth's climate naturally oscillates between warmer interglacial periods and colder glacial periods. Geological history shows clearly that ice ages eventually end, transitioning back to warmer climates. Understanding these realities helps dispel confusion, ensuring informed conversations about Earth's climate future. Accurate knowledge enables better preparedness and rational planning for all potential climate scenarios, including rapid cooling events. Preparing for a potential ice age, practical steps we can take. If rapid global cooling or a modern ice age occurs, practical preparedness becomes crucial. At an individual level, experts recommend developing greater self-sufficiency through practices like gardening, preserving food supplies, and learning basic survival skills. Investing in energy-efficient homes and renewable energy sources, especially solar with battery storage, helps maintain essential utilities even under extreme conditions. Communities should prioritize resilience by diversifying local food production methods, including indoor vertical farming and greenhouse agriculture. Strengthening infrastructure to withstand extreme cold, including insulated buildings, reliable heating systems, and robust emergency communication networks, is essential. National governments must proactively prepare comprehensive contingency plans addressing agricultural failures, energy shortages, and mass migrations. Strategic food reserves, climate-resilient infrastructure investments, and international collaboration on migration management are crucial elements. Experts strongly recommend robust funding for climate research, agricultural innovation, and sustainable energy solutions adaptable to sudden cooling scenarios. While the probability of a rapid cooling event remains debated, comprehensive preparedness remains wise. By embracing proactive strategies, individuals, communities, and nations can significantly mitigate potential impacts, ensuring resilience in the face of Earth's unpredictable climate future. Ultimately, awareness and preparedness empower humanity to navigate any climate challenge, whether warming or cooling, ensuring a sustainable and secure future for generations to come.